is, I think, or the continent is basically the blue part, the ocean is basically the red part, I believe, in this case. And here's an example of the MOHO depth, which is basically a transition from ductile to brittle flow, or ductile to brittle materials. Okay, here's an example of a two-dimensional line over a massive sulfide deposit. And the sulfide deposit has a density of 4.4 grams per centimeter. The volcanics and sediments on either side have a much lower density. And then there's some little slivers of iron in here as well. So what you can see here is the observed gravity and the modeled gravity. Again, remember when we talked about model to data? What we're doing here is we're putting in a hypothetical model of the density distribution. So we're saying we think that the density profile looks like whatever it looks like. You know, it's a picture of density. Maybe it looks like this. And then we're running a computer program that models the gravity data that we would collect on the surface for that particular model. All right? So that's almost, if you think about it, like GM equals D. We're transforming the model into data that we record. So in this case, what we've done is here's our observed gravity profile. That's data that we collect in the field. And then we're basically putting some low density fill, not even low density. We're basically just putting, actually here, I'm not sure what it is here. We're basically burying this whole deposit below the surface of the Earth, right, and putting something in between. And what you see is if the massive sulfide goes to the surface, we get a larger response. And as we bury that deposit deeper and deeper, the response gets weaker, but it also gets smoother. Okay? And that's because the gravity has an effect on larger areas. If we look at the simulation of gravity, it's going to have less of an effect. Here's an example from a salt dome. Yeah. Okay, the model is typically created, that's a really good question. So how would we generate a model? Okay, so let's say that we have zero depth of burial. And let's say that we have a massive sulfide deposit. Right? And this is, so in the computer, how would we generate this model? What we might do is discretize little boxes. And we just say, okay, this box has density of x1, y1. Okay. This box over here has density which equals, what is it, 2.9. This has density of x10, y1, which is equal to 4.4. And then obviously some kind of intermediate thing here might have density of x15, y1 of 3.2, kind of averaging the different areas in those boxes. So this becomes a two-dimensional array of density values. And then as we'll see, we can actually measure the acceleration of gravity as gm over r squared, right? Where r is the distance from our particular gravimeter. Here's our gravimeter. So this is at a particular, in this case, x0, right? This is y equals 0 on a particular x. So we measure this, and we can calculate this, right? This is simply the distance from the center to that particular sensor.
So is the model using the data from the observed?
Pardon?
Is the model using the data from the observed?
No. The model is literally just putting something like that in, and then running that equation Yeah, the model is something you make up. Say, oh, I think it's this. You've heard the story about the geophysicist, the geologist, and the petroleum engineer, haven't you? Did I tell you that one? Okay. So the manager comes to the different geoscientists and engineers, and he says, "What's 2 plus 2?" The engineer, back in the old days, would get out his slide rule, but now he gets out his Excel and he types it in. And it's, well, it's 4. 4.000000, maybe 3.99 to 10 to the 26th accuracy, depending on whether we're double precision or single precision. Then he goes to the geologist and he says, "What's 2 plus 2?" And the geologist takes out his Brunton compass and he kind of measures a little bit like this. He says, "Well, it's somewhere between 3 and 5. And then the manager comes to the geophysicist and he says, "What's 2 plus 2?" And the geophysicist says, "What do you want?" And that's part of the art of geophysics. The way these models, particularly gravity and magnetics, are non-unique. In other words, we can get the same gravity data from many different models. That's where the geology comes in. So we have to kind of know what kind of geologic problem and what kind of characteristics we're looking at in order to interpret the gravity data correctly. But very good question. All we're doing is basically doing something like that. This is all in the computer, and it's like, well, I think the model might look something like this. And then I'm basically iteratively changing the depth until I get a good fit or a good visual fit. Now, I can also make that fit mathematical, right? And I can automatically, if I have a starting model, I can automatically change the values. And that's what's called gravity inversion. So the computer figures out, if I have a starting model, let's say I started the whole model with a constant density, but density didn't change, all right? That's how I start, and that's basically, I'm agnostic about the real model. Now what I can do is I can match the model data, which is a straight line now, to the data. And I say, well, that kind of fits some places, but then there's this big thing. How will I adjust the model in order to fit the data? And that's where a computerized inversion comes in. And there are huge number of papers and studies associated with exactly how you do that. And that's basically the idea of what do you want it to be? How do you get from that model to the data? And I think of it as really learning how to divide by 0. Okay, because that's what we're really trying to do. We don't have a problem that's truly mathematically solvable, and we have to cheat. And that's really, so geophysicists are cheaters too. They basically try to get around the fact that you can't divide by 0. So they divide by very, very small numbers instead. Okay, so this is an example of a salt dome. Salt domes are important because oil sits on the sides of these salt domes. And the salt is actually less dense than the sediment around it. And so if we're looking at the pull of gravity over the salt, we're going to actually see less of a pull at the salt dome than we are in the sediments around it. And we can use kind of this break in the salt profile as an estimate of where the salt dome stops. And again, what we're going to do is we're going to put in a model of the salt dome and see how it actually matches our data, right? And what that will tell us is hopefully some estimate of the width of the salt dome and actually where the salt dome goes, how close it goes to the surface, okay? Salt domes are pretty interesting. The Gulf Oil Company, which was purchased by Chevron many, many years ago, actually centered in Pittsburgh, Pennsylvania. Gulf stands for the Gulf of Mexico. And Gulf found a lot of large oil fields with this technique back in the late 20s and 30s. And it actually made their company. Gravity methods were responsible largely for the value that Gulf Oil Okay, here's an example of a more micro gravity survey. So here you have two voids with 0 density, and you have maybe granite, 2.71 density around it. And you're running a survey across the voids. And you can see that at each void, here's the gravity measured data, the dots, and the model that you've created to fit the data. And again, if you move this void up, you get more of a deflection, and you say, well, that's not the right model. You move it down too far, you get less of a deflection, and you say, well, that doesn't fit the model. So you're basically moving these things up and down. Again, you can do it by hand. You can just basically play with the model, or you can do it in the computer. Here's an example from a church. And they were looking for a burial site. They were basically looking for a tomb under the church. So they made gravity measurements where they could on the floor of the church. And they found, this represents less gravity pull, they found a hole almost right underneath the nave of the church. Sure enough, when they went in there, they found a